This conference will now be recorded.
Hello everyone, today we are starting a new chapter which is D and F block, and here first we will see some idea about the periodic table, and after that there will be discussion regarding to D block elements, and after finishing D block elements there will be F block elements, and in D block elements first we will see what are the trends in different atomic properties, that is atomic radii, ionic radii, density, ionization energy, etc. So in periodic table there are mainly 4 blocks, okay, that is P block, D block, S block and F block, okay, and total elements in the whole periodic table, this is 118, and it is arranged, that is if you consider modern periodic table, it is arranged according to increasing atomic number. Now P block we have already seen, there are total 6 groups starting from 13 up to 18, okay, 13, 14, then 15, 16, 17 and 18. And S block there are 2 groups. So in between S and P there is presence of D block which is in purple color. Now in D block, if you consider 4th period, this is 4th period, this is 5th period, okay. So in these 2 period there is no F block elements, but after 5, when we are now in 6th period, now after lanthanum it is not directly hafnium. In between these 2 elements there is presence of all these 14 elements, that is starting from cerium up to lutetium. But why we are not placing it in the periodic table? Because if you place all these 14 elements in the periodic table will be very wide, and handling of periodic table, that will be very difficult in day-to-day life. So that is why it is placed below the periodic table. And after actinium, it is not directly Rutherfordium. In between Ac and Rf, there is presence of all these 14 elements, which is also part of A block. It is starting from thorium up to lawrencium. So only in 4th and 5th period there is no block elements, but in between La and HF there is 4F block, that is this one, which is 4F, and then 5F. Now what is the, that is on the basis of which we are having here total 4 blocks? It is actually depending on the valence electron. So when you are considering S block elements, the valence electron is present in S. Then in P block elements, valence electron that is present in P, and not just valence electron, it is also that in which orbital there is gradual feeding of electron. So in P block, that chapter we have just finished, there we have seen that it is filling as if from NS to NP1 starting from group 13, which is this starting from boron, aluminium, gallium, indium, helium, and up to 18 where it is now NS to NP6. That means gradually the electron is filling in P orbital. P1, then in case of group 14 it is P2, then P3, P4, P5 and P6. So as the gradual filling of electron in P block, so that is why in P orbital, that is why all these elements are under P block. Similarly, when we are talking about D block, the gradual filling of electron, that will be in D orbital. And here group number is starting from 3. So in 3 there is scandium, yttrium, lanthanum, and ending at 12. So from 3 up to 12, all these groups are present in this D block. And after finishing D block, then we will start the discussion of 4F block and 5F block. So 4F block, that is also known as lanthanides elements, and 5F block, that is actinide elements, okay. And in this case, as it is we are calling it 4F block elements, that means gradual filling of electron, that will be in the F orbital only. So in this it is a very simple picture of periodic table where you can see only the no elements are mentioned, only the blocks are highlighted here, okay. So when it is D block, which is basically starting from 4th period, so when it is 4th period, here gradual filling of 3D orbital will take place. Then when it is 5th period, then electron will be filled gradually in 4D, then 5D and 6D, okay. And F block that is present in between these two elements. Okay, that is already mentioned. So any doubt in this table? So now we will see the D block elements in detail. So here we do not have the whole periodic table, we have only the D block elements and F block elements. Fine. So D block element, this is group 3 and up to 12. It is starting from atomic number 21 and then gradual filling of D, and we are reaching up to atomic number 30. And just after scandium in the same group there is yttrium, and after that there is La. Now in the fifth period also see 39, 40, so it is gradual. But when you are now here after 57, it is 72. That means starting from 58 up to 71, all these 14 elements that you will find here, which is basically the 4F block elements. Similarly, after AC, after that, that is 89 atomic number, next element is 104, that is mentioned in the periodic table, which is rutherfordium. But in between actinium and rutherfordium, there is atomic number up to 90, then up to 103. So all these elements that is represented just below the D block elements. Okay. Now here, if you can remember any which element is present in the same group. So for example, if I say if it is third group, then the elements will be scandium, yttrium, and then lanthanum. Now just remember the atomic number of the first element, because if you can remember the atomic number of the first series, then you have to just add 18. So what I am trying to say, so it is 21. So the next element that will be 21 plus 18. That means now it is 39. Similarly, if you want to know the atomic number of the next element, what you have to do? You have to now add. It is not 18 anymore. Now you have to add 32. So now it is, sorry, it is again 18. So what you are getting 57. But this is true only for the third group, because now if you move to fourth group or fifth or sixth, just take this one, which is 4, 5, 6, 7. Okay, so in 7 period, first atomic number it is 25. So the next one, which is 43, how we will get it? 25 plus 18. So this is 43. Okay, TC. And the next element 75. Now 75 you cannot get simply by adding plus 18. Okay, because if you just add it, you will get 3 and 8, it is 1, it will be 61. Okay, but actually see what is mentioned is 75. That means basically you have to add 14 more, then only you can get this number. Now why it is so? Because if you consider group the first group in the D block, there is no 4F block elements. Okay, so that is why it is, the gap is 18 and then again 18. And why it is 18? That is also easy to remember, because in the total D block, here total number of electron involved 10, because maximum capacity of d orbital is 10. And after D block there is P. So when you are starting from SC and ending at Zn, then there is the next elements present in the P block. And in P block 6 more electron will be filled. And then when you are again coming back in the second period, it will be total electron 10 plus 6. But it is 16. But 2 electron you also have to consider in the S block. So now it is 16 plus 2, that means 18 electrons. So that is why when you are moving to next element, you have 18 gap of 18. But as between after third group, when you are switching to fourth group, now between La and HF there is 14 element present. So that is why simply adding 18 electron, it is not enough. Now you also have to add 14, because all these elements, there are total 14 electron gradually will be filled, because in 4F, not 4F, that is in F, maximum capacity is 40. So that is why now, except the first group, when you are considering the other groups, the gap will be 18 plus 14, which is basically 32. Fine. So the elements in the periodic table belonging to group 3 up to 12, they will be called as d block elements. And the reason is, in these elements, the last electron is entering in the penultimate d subshell. Now, penultimate d subshell, what it means? Because see, here, this is actually fourth period, okay? Then fifth period. Now, fourth period means what? The last orbital where that is, which is 4s, okay? When we will see the electronic configuration, it will be clear. So, as it is fourth period, that is principal quantum number is 4. But what will be the penultimate? Penultimate means just the previous shell. So it will, if it is principal quantum number n, then penultimate will be n minus 1. That means 3. So when it is fourth period, it is involving 3d electron. When it is fifth period, it is involving 4d electron. When it is sixth period, it is involving 5d electron. Okay, so that is why the last electron is entering in the penultimate d subshell that is mentioned here. So the first series that will be called 3D series, because electrons are gradually filled in 3D. It is starting from scandium up to Zn, and then the second one 4D series, which is starting from yttrium up to cadmium. Then 5D series. Now see, when it is 5D series, this fourth period, this is fifth. Now when you are in sixth series, that sixth period, and 5d electrons are gradually filling, then it is starting from La up to Hg. But remember, omitting cerium to lutetium. That means these 14 electrons you do not have to consider, because they are under F block. Similarly, when you are now at the last period, 7th period, and 6d electrons are gradually there, that is filling, then it is RF2, basically it will be, AC2CN. It is AC2CN, but remember, there will be gap of thorium to lawrencium. That means starting from thorium up to this, you have to omit. Rest of the elements, they will be under D block. Okay. A transition element, see this is a new term that we are seeing here, transition element. Now it is defined as the one which is having incompletely filled d orbital. Now d orbital maximum capacity is 10 electron. That means when it is up to 9, starting from d1, d2, d3, in this way, when you are reaching d9, then also it is not fully filled. So they will also be called transition element. But when it is D10, now it is completely filled. You cannot say that it is incompletely filled in its ground state. So that is why this is actually not transition element. So according to this logic, Zn, zinc, cadmium and mercury, these three should not be considered as transition element. But what happens? Although electrons in group 12 means Zn, Cd, Hg, they do not fill the d orbital because it is already D10. But their chemistry, it has similarity with the other members. So that is the reason they are also considered in the D block elements. Fine. After D block, now we will see the electronic configuration. General electronic configuration for D block elements, n-1 D to the power 1 up to 10. That means gradual filling of the electron, and ns1 to 2. So sometimes you may find in some cases, at least it is in 2 cases, where it is ns1. Otherwise, it is always ns2. So if n value principal quantum number, just consider the first series. If it is 4, then this will be 3. That means 4s, and this is 3d. Or if it is 5s, it will be 4d. If it is 6s, it will be 7d. If it is 4s, then 5s, then 6s. So if it is 6s, it will be 5d. Now individually, if we see for fourth period after argon configuration, because if you consider the previous period, which is third period, it is ending at argon, atomic number 18. After that, it will be 4s 1 to 2, 3d 1 to 10. So this is for the first transition series, or it is also called 3d series, scandium up to Z. Then the fifth period, this one, this is fourth, this is sixth. In the fifth period, now there is krypton 5s starting from 1 up to 2 electron, and now it is 4d. So say this is very simple. Just it is increasing one by one. 3d, 4d, 5d, and 4s, 5s, 6s. Fine. And period 6, sixth period after xenon configuration, which is noble gas, it is 6s 1 to 2, 5 to 1 to 10. So this is individual electronic configuration, but this one is the general electronic configuration. And remember, though after 5d series there is another period, but mostly we will limit our discussion up to this, not 6th period. Sorry, not 6d series. These 3 series will be mainly discussed. Here we have all the elements of the 3d series only. See, starting from scandium up to Zn, and this is the atomic number Z, then 3d orbital and 4s orbital. Now atomic number 21, after argon there will be only one electron, because argon is 18, and after argon there is s block elements, two s block elements, that is 19 and 20. That means potassium, calcium, these two will be just before scandium. So that is why now atomic number, it will be 21. That is after argon there will be 19, which is for potassium, 20 for calcium, and 21 that will be for scandium. So only one electron in 3d, and 4s, this is always 2. And next what we will see, 22, that is argon again, but now one electron is extra. Here we do not have any change. And remember, among 3d and 4s, why we have electron already filled here, because that is dependent on n plus l rule. Now n plus l rule says, first we will find out the n plus l value. So for 3d, n value is 3 and l value, that is the another quantum number, azimuthal quantum number, that is for d, it is 2. So it will be 5. But when it is 4s, if you consider the n plus l value, this is 4, and l is 0 for s orbital. So this is what the final value you are getting, 5 for 3d, 4 for 4s. So when it is less, that orbital should be filled first. So according to this rule, 4s is filled first, and after that 3d is filled. Then when we are vanadium, having vanadium atomic number 23, one more electron. Now the next one, there is some discrepancy you can find. The next element, our expectation is it should be up. This electron should not be here, it should be here, right? But what happens here, instead of writing 3d4, if we are writing 3d5, then it is stable half filled configuration, and that is the driving force that now instead of writing the electron here, we have placed the electron in 3d. After that, so the discrepancy, it is at chromium, and the same thing you will also notice at copper. So when you are having nickel, see the next electron, what we expect, it should be here, but here we should not get any pair. But see, now instead of the configuration 4s2 3d9, what we are having, we are not having this, but we are having 3d10 4s1. Why? Because this one is more stable, 3d10, that means fully filled configuration. So this is the reason that for copper and chromium there is some little bit difference that you can find. And rest of the elements, that is, there is no problem, it is filling gradually one by one in 3d orbit. Fine. Now we will discuss different atomic properties, and the first property here we have atomic radii. Now, when we are saying atomic radii, obviously we have to consider atom. There is another term which is ionic radii. So when it is ionic radii, then you have to consider some charge over the elements. Okay. So first we will see when they are neutral atom, how the atomic radii is changed. The atomic radii first decrease till the middle and then it becomes almost constant, then increase towards the end of the period. Now here the green line that is for first transition series, the blue line that is for second, and the red line that is for the third series. Okay, and in the y-axis we have all the radius values in nanometer unit. So see, for all the three series, first there is a decrease, then if you focus on the middle part, it is almost constant, right? Then again there is increase. So this is observed as we are observing the trend. But we have to know what is the reason behind it. Why it is not gradual? Gradual means why it is not gradually decreasing. Why first decrease, then again increase. Okay. So there must be two different types of factors are operating, and these two factors must be opposing to each other. So that is why sometimes one factor is winning over the other and vice versa, and we are getting this type of trend. So nuclear charge increases each time as a new electron enters d orbit. So when you are moving from scandium to titanium, or you can also consider the other series, then what is happening? Atomic number is increasing and one electron is also increased. That means both nuclear charge as well as the electron number both are increasing. So this new electron which is entering d orbital and shielding effect of d orbital, it is not very good. So as shielding effect is not good, so the positive charge which is present in the nucleus and the outermost electron, this attraction that will be very high. So as a result, the size will decrease. Okay. So because of this reason, when you are moving from scandium, or if you consider the other series, see up to this part, there is gradual decrease, right? So higher is the, you are adding the number of electrons because gradually there is atomic number increasing. Okay. So because of this poor shielding effect of d electron, now the attraction of positive charge, that is the nucleus or the outermost electron, it is very high, so size is decreased. Hence the net electrostatic attraction between the nuclear charge and the outermost electron increases and atomic radii decreases. So this is the first reason for which there is decrease. But there must be some other factor operating for which now it is again increasing. Okay. Now what is this second factor? So see this table we have already seen in the last slide, but again I have this here because see, as we are moving from left hand side to right hand side in the periodic table, that is from scandium, when you are moving towards Zn, gradually the number of electrons are increasing in the d orbital. Okay, so what will happen? Now there will be electron-electron repulsion. So this type of repulsion, that is not very high up to the middle part, but as you are moving towards the other extreme, that is the right hand side, now electron repulsion factor also you have to consider. So this electron repulsion, it will be so high that they will try to move apart from each other, and as a result atomic radii will increase. So for this factor, when you are at the right hand side extreme, now size is increasing. So increase in atomic radii towards the end, it is because of the electron repulsion. Why? Because more is the pairing of electrons occurring. See, up to this part there is no pairing, but as we are moving more from Fe to CO2 Ni, now there is electron pair increasing. So that means repulsion will also increase. The repulsion interaction between the paired electrons, it will cause increase in atomic radii. Okay, so these are the two different reasons for which we are seeing this type of trend. And this factor, suppose this is the second factor, this is the first factor. The first factor is poor shielding effect of d electron, and the second reason is electron-electron repulsion. Now these two opposing factors, when they are completely nullifying each other, that part is basically this part. See, it is almost same. If you draw a line on the y-axis, it is almost 13 point something. So these elements in the middle part, they will have almost same atomic radii because the two opposing factors are compensating each. So is there any doubt? Should I repeat any part? Now after atomic radii, next we have to see ionic radii. Now when we are saying that ionic radii, obviously we have to consider some ion. Now as D block elements are mostly metal, so we have to consider positive charge. So now it will be written as M2 plus. Though there are different oxidation state possible, but we will consider 2 plus only because this is the common oxidation state. Now see, we have only the first series and ionic radius mentioned in picometer unit, and here starting from calcium is also there, though you don't have to consider it. It is not from D block, it is from S block. So scandium 2 plus, that will be somewhere here. So increasing atomic number starting from scandium up to Z. So see, in the previous that is atomic radii, when we have discussed that it is just like a half circle type. Okay, but now as if there are two circles, that is this type. But we have to know what is the reason. But see, if you do not consider these elements, that is if you consider only Ca2 plus, which is basically 3d0, there is no d electron, it is from S block, and 4s2. Then if you consider Mn2 plus, this is basically 3d5. Sorry, 4s not, it is not 4s2, it is actually 4s0 because it is calcium 2 plus. That means 2 electrons lost. Similarly, when it is manganese, it will be 3d5, 2 electrons lost from 4s, and for Zn it is 3d10. So see, if you consider only 3d0, 3d5, 3d10, that means either there is no electron, or it is fully filled, or it is half filled. So only in these three cases, if you consider the elements and if you are joining the line, you will get a straight line like this. But if you are considering the elements in between, now you are getting a hump type of nature in the curve. We can expect decrease in the ionic radii of N2 plus and smoothly from Ca2 plus to Zn2 plus because of increase in nuclear charge. So we can expect that it will be smooth decrease like this if you consider the graph. But actually that is not so simple. So what happens here? For weak field ligands, though some terms now I will use, which is basically from coordination chemistry, which is completely different chapter, but still we have to have some idea about the crystal field splitting. Otherwise, we will not be able to understand why we are getting this type of two hump curve. Okay, so that is why some crystal field theory we have to discuss. So weak field ligand. Now there are two types of ligands. And here we are considering metal ion. Now metal ion, when we are saying, obviously it cannot remain in free state. It must be associated with some ligand. If you are considering this in ionic solution, then it will be associated with some water molecules like this. So 6 water molecules, and suppose there is M2 plus charge outside because water is neutral. It may be any other ligand also. Suppose metal is attached to cyanoligand. So different types of ligands will be attached. But we are here writing only metal 2 plus. But remember, it cannot be remaining as free metal. Now there are two types of ligands. One is weak field ligand. So those ligands that are interacting with metal positive center, if the interaction is very weak, then the ligands will be called weak field ligand. And if the interaction is very intense, then it will be called strong field ligand. That is the difference. But this plot, this is specifically for weak field ligands. Remember, if you are taking any strong field ligand, then the nature of the curve will be something else, and that is beyond scope of our syllabus. That is not required. Just see for weak field ligands, how will be the nature, that is enough for us. Okay. So the plot that you are seeing here, that is actually for weak field ligands. Now this indicates that the expected regular decrease that is absent except for these three cases. Three cases means 3D0, 3D5 and 3D10. So except these three, that is, if you consider only these three, you will get a gradual decrease. But why for other cases we are not seeing this, that we have to discuss. Some divalent ions fall below this curve. That means if you consider this dotted line, they are falling below this curve that is mentioned here. Now why it is so? Because they have asymmetric distribution of d electrons. Now what is the meaning of this asymmetric distribution? That we have to understand. Now until now what we know, that d orbital, there are total, that is maximum capacity is 10, and we write it in this way, right? And what we are considering here, that all these 5, they are having same energy, okay? But actually in presence of ligand, it may be any ligand, water, chloride, cyano, what happens? Now the energy of these 5d orbitals are not same. So degeneracy is lost. The meaning of degeneracy is when all are having same energy, but if they are not having same energy, that means degeneracy is lost. But why degeneracy is lost? If we want to understand that, for that you have to first know what are the shapes of different d orbitals, because these 5d orbitals are basically dxy, dxz, dyz, dx square, y square and dz square. So how these 5d orbitals they look actually, that we have to know. Then only we can understand why in presence of ligand these degeneracy of 5 orbitals are lost. So before going into the discussion that is written here, I will like to mention the shape of different d orbitals. So see, when it is dxz, here you can see the lobes. This is x-axis, this is y-axis, sorry, the xy, and this is z. So all the axes they are 90 degrees to each other. So when it is dxy, it will be in the plane of xy. See, it is the plane of xy. But the lobes are in between the axis. That is, this is one axis, this is another axis, and the lobes are in between the axis. Similarly, when it is zx, now this is x, this is z. When it is yz, now z and y. So yz is in yz plane, then xz it is in xz plane. Fine. So these three you can find some similarity. But if you consider dz square, now it looks completely different. Okay, so dz square, that is, here the lobes are directly on the z axis, and when it is dx square y square, it is true that they are in the plane of xy, but see, it is not same as dxy. What is the difference? In dxy, lobes are in between the axis, right? But now it is directly on the axis. See, so this is the difference. So now we will divide all these 5d orbitals in two categories. So in one category, you will have all these 3d orbitals, and that category will be called as T2g. Another category where the lobes are directly on the axis, and this category will be called EG. Now these EG and T2g terms that are mostly used for octahedral geometry. Okay. Now what is crystal field splitting? Again, I am saying this is completely from different chapter, but if we do not have some primary idea about this theory, we will not be able to understand why the ionic radii, that is in the previous slide that you have seen, why the nature of the curve is like this. Now, as I have said that these two groups that we have made, EG and T2G, that is for octahedral geometry. So in octahedral geometry, suppose this is ML6. So metal, that is in octahedral geometry, this is the central atom, and 5 ligands are approaching from different axes. So there will be x-axis, z-axis and y-axis. Though it is written in this way, but you can also write this is as x, this is as y, and this is as z. But that is not important. The important thing is here octahedral geometry present. And one important thing that you have to notice that all the ligands that are approaching towards the metal, see, in this way, that is directly along the axis they are approaching. So these two ligands, they are approaching along y-axis. These two ligands, they are approaching along the x, and these two along z. So I'm trying to say that all the 6 ligands, they are approaching along the axis. Now, why I am that is giving, let me change the color. Why I am focusing on this part so much? Because for T2G category, the lobes are not along the axis, but ligands are approaching along the axis. So when the ligands will approach, the interaction between T2G d orbitals and ligands, it will not be very intense. But if you are considering the d orbitals under EG category, now the lobes are directly on the axis, ligands are also approaching along the axis, so there will be face-to-face interaction, direct interaction. So that is the reason now the degeneracy is lost. These two d orbitals will have higher energy, and the 3 orbitals that are under T2G, they will have lower energy. So degeneracy is lost. Electrons in dz square and dx square y square orbitals that are lying along this axis, they will experience greater repulsion because ligands, they are approaching with electron density. And in metal also there is some electron density. So between these two electron density, there will be some repulsion. That means interaction will be direct. Now look at this picture. So this picture is on the basis of crystal field theory, which describes the breaking of orbital degeneracy. That means previously in absence of ligand, you have all these 5 d orbitals, all are having same energy, right? So see, when it is free metal, suppose it is simply M2 plus, all the d orbitals are having same energy. But now when it is in presence of ligands, there will be 2 different categories. One is EG, T2G. Now T2G is lower in energy, EG is higher in energy. In between these two situations, you can also see here all the d orbitals are having higher energy compared to previous situation, but still all are having same energy. So this is actually the average energy of d orbitals in spherical crystal field. So this is actually an imaginary situation. Suppose the ligands are approaching in spherical crystal field. That means it is symmetrical in nature, but in reality it is not so, because when the ligands are approaching, they are not facing similar environment. So that is why we cannot consider spherical crystal field. It is actually the imaginary case. So what you have to actually consider is this part where degeneracy is lost. So this is free metal ion, but here we have all the ligands, and see if the gap between EG and T2G we are considering Delo, then this part is 2/5 of Delo and the upper part it is 3/5. So it is not exactly equal. 2/5, 3/5. Now when it is D0 system, that means you do not have any D. So no question of crystal field splitting energy calculation. So crystal field stabilization energy, in short we call it CFSE. So CFSE, how we can calculate, I will show it now. So for D0 system, no calculation is possible, right? But suppose it is 3D5. Remember, for Mn2 plus system, it is actually 3D5. Now how we will place this 3D5 for weak field? For weak field, the placement of electron is like this. So we do not do any pairing in T2G. Now, if it is asked calculate the CFSE, then it will be done in this way. 3 electron in T2G, so 3 into 2 by 5. Now as it is lower in energy, there will be a minus sign, and 2 electron in EG, so 2 into 3 by 5, and there will be positive sign. So minus 6 by 5 Delo plus 6 by 5. So it will cancel each other. So ultimately there is no crystal field stabilized energy gain. Similarly, if you do the calculation for 3D10, you will see again you are getting CFSE 0. So for 3D0, 3D5, 3D10, CFSE is not, you are not getting any value. So that is why for these three cases, you are getting this type of smooth decrease. But for other system, Sc2 plus titanium 2 plus vanadium 2 plus chromium 2 plus, now there will be some CFSE value that you will be getting. And because of that, they are not in this smooth line. Now we will see what is written here. T2G orbitals, they are directed between the axes. That is, the lobes are directed between the axes, right? And the d electrons are unable to shield the ligands from the nuclear charge because the lobes are not facing the ligands. So the ligands will experience higher effective nuclear charge because they are not able to shield than predicted. As a result, ML distance will be short. Ionic radius will be smaller than expected. Now suppose if instead the electrons were distributed uniformly over all 5 d orbitals, that is, if the electron distribution it is symmetrical, in that case they will be much more effective at screening the ligands from the nuclear charge. But that is imaginary situation, that is not actual situation. So that is why if that happens, then it will be longer, but actually that doesn't happen. So that is why it is short. Now this is all about T2G orbital. What about EG orbital? Now when it is EG, now the lobes are directed along the axis and point directly, that is, they are facing the ligands directly. So there will be repulsion between the metal electrons and the ligand electrons. As a result, there will be increase in metal ligand distance. That is, ionic radius will increase. So when there is electron in T2G, there will be decrease. When there is in EG, there will be increase. So the combined effect of these two, it will be ultimately such that the nature of the graph that we will get, it will be like this. But still, if you have any doubt, that will be completely, you can understand, you will have a clear picture when we discuss the actual chapter where this crystal field splitting is discussed. This is actually not part of D block, but for coordination chemistry, we mainly discuss that. But here we are just having a primary idea about the CFT theory, because if we do not know that, why we are getting this hump type of curve, that we will not be able to understand. So remember, for these three systems, this is just falling directly on the smooth line because there is no CFSE involved. But for other elements, there is some value of CFSE for which they are below this line. Okay, so any part should I repeat? Now after atomic radii and ionic radii, how it is changing along the period as we are moving from left hand side to right hand side. Next we will see how the density is changing. Here we have this graph where density in gram per centimeter cube is mentioned in y-axis, and here we have the group number. Here the group number is starting from 1, 2, but these two are actually for S block. But our concern is only from group 3 up to 12. Even 13 is not required. So just focus on this one. Scandium 2Z. Now density means mass per unit. Okay. Now volume is directly related to radius. So when R is increasing, volume is also increasing. Density is related to mass of an object and also volume. Now what we have seen, just consider period 4, that is the fast transition series. When we have moved left to right across the period, the mass of the atom is increasing because atomic number is increasing. That means here numerator is increasing, that is M is increasing. Now next we have to consider volume. Now volume is related to radius. In terms of atomic radius, what we have seen, the radius decreases, but there is not any uniform manner. Remember, this type of nature we have seen for atomic radius. So what happens, that is the overall effect, M is increasing left to right, that is fine. But V, sometimes it is increasing, sometimes it is constant, sometimes it is decreasing. So this is not gradual. So when M is increasing, D will increase, but when volume is increased, density will decrease. So the combined effect is such, that is when we are combining these two effects, these two general trend, that is one trend is for mass, another trend is for atomic radius, which is nothing but related to volume. So these two general trend, it create a trend of increasing density as we move across the period. But see, though we are saying it is increasing, but actually it is not very smooth. So there is increase up to chromium, it is smooth, but after that there is increase, but still there is no particular nature, it is not smooth. Fine. It is because of these two general trends. Sometimes mass is overcoming over the volume factor, sometimes volume is overcoming the mass. Now depending on this density factor, we have a problem here. What is the correct order of the following elements with respect to their density? So here we have only 5 elements. That is chromium, then we have Zn, we have copper, iron, and cobalt. So after iron there will be cobalt. So from this graph, it is clear that copper is having maximum density, isn't it? So if copper is having maximum density, suppose it is, I can understand that it is really not possible to remember the actual trend. But what you can remember is that which element is having maximum density, that is easy to remember. Now if you look at the options, see only in option 3, copper is having highest density, but in other options, copper is not present. So just on the basis of this information, that copper is having maximum density, even if you do not know what is the trend, but still you can choose the correct option, which is option 3. So from the graph it is clear, but after copper it is mentioned cobalt. Okay, so this is the position of cobalt. After cobalt it is chromium and iron. So chromium and iron is little bit greater than chromium. And chromium and Zn both seems as if both are having same value, but actually there is slight difference. Chromium is slightly having greater density than Zn. Here we have the actual values, but all the elements are not required. Zn, copper, cobalt, iron, chromium. So the first one is copper having maximum density. After copper, it is actually nickel also having almost same, but we are not considering it. It is not present in the question. Next one is cobalt. See, then iron 7.9, and after iron, in between chromium and Zn, both are actually have. So it will be 2, not 1. So both are actually having almost same value. So that is why it is from the graph it seems as if same, but actually it is slightly different. Okay. So correct option is option 3. So is it clear why how we can choose the correct option? Just on the basis of the fact that copper is having max value. Any doubt? Ionization energy. In P block you have seen there is very smooth decrease down the group, right? But now in case of D block, mostly we in P block what we have done, we have considered individual groups, that is group 13, group 14, group 15, like this. But see, in case of S block also we do the same thing, that is group 1 lithium, sodium, potassium, etc. Then group 2 magnesium, calcium, etc. But when it is D, see, we do the discussion differently. Now we do not consider individual groups. That is, we are not considering group 3 and then we are doing the discussion, then group 4 doing the discussion. No, it is not like that. Now what we are doing, we are considering each period and we are trying to see how it is changing. Okay, so try to understand the difference. So when we will discuss ionization energy change, it is not down the group how it is changing. It is along the across the period, left to right. So when you are moving from left to right, effective nuclear charge will increase. The greater the effective nuclear charge acting on the electrons, greater will be ionization potential, because when nuclear charge is very high, removal of the most loosely held electron, it will be very difficult, right? So that is why ionization potential will be maximum as you are reaching at the right hand side extreme. Okay. The fast ionization energy of transition element, they will be higher than those of S block, because if you consider the periodic table, first left hand side we have S, then D, then P. So we know that as we move from left to right, nuclear charge becoming high and high, as a result ionization energy is also increased. So that is the reason, if you consider same period and if you are comparing ionization energy with respect to S block, obviously for D it will be high. So that is mentioned here, the fast ionization energy of transition metals are always higher than those of S block elements, but it is lower than P block, and that has to be because P block is coming after D. So they are on the right hand side of D block element. So that is why it will be lower compared to P orbital. Now in a particular transition series, because there are total 3 series, 3D series, 4D series, 5D series. Ionization energy although increases gradually as we move from left to right, but the increase is not appreciable. Now look at this picture. The green line, that is for it is 3D, it is not 5D. The blue line, that is for 4D series, and the last line, that is the pink one, that is for 5D. Okay. So the green line, if you observe, it is starting from titanium, then there is increase, though after iron there is again slight decrease. So it is not very smooth. Okay. And similarly for other two also, there is increase, but increase is not appreciable. So here in the same graph, we have ionization energy trend for all the 3 series. This is first series, this is second series, this is third series. Fine. Now another graph we will also see, where we have only ionization energy of first transition series. See, we have only scandium up to copper. And what we are comparing? We are comparing here the first ionization energy, the second ionization energy, and the third ionization energy. So when it is fast ionization energy, that means you are, suppose just take copper, you are removing one electron. By applying fast ionization energy, you are getting copper plus. Then again you are removing another electron, now you are getting copper 2 plus. Then third ionization energy, you are removing the third electron, now it is becoming copper 3 plus. So the first electron removal, it is always easier process, because in the second one you are removing electron from already electron deficient species. So it is obviously difficult process. Then the next one, now you are removing electron from 2 positive charge containing species. So this is more difficult. So that is why third it is higher than second, and first second, that is higher than first. Okay, and this is also true for the other 2 series. Now the value of second ionization energy for chromium and copper, see there is something we have to mention. Second ionization energy for chromium, this one, and for copper, these two are comparatively high. See, there is a slight peak you can observe. Now why it is so? Because chromium, what is the configuration? Configuration is 3d5 4s1, and for copper it is 3d10 4s1. Now second ionization energy means what? First ionization energy, you have already removed this electron. Second ionization energy, you are removing electron by breaking the stable half filled configuration. Similarly for copper, when you are removing the second electron, you are breaking the stable fully filled configuration. So that is why here the process will be difficult. Extra stable configuration, half fill, full fill. So that is the reason now you are getting some higher value. Okay. So any doubt in the ionization energy trend? Next we will see metallic character, because the elements that are present in D block, they are mostly metals. But don't think that their metallic character is like S block metals, because in S block also the elements are metal. Okay, but compared to S block metals, these D block metals, they are not very so reactive. Okay, they are less reactive. They are hard, malleable, ductile. So all these are basically characteristic of metals, and it is because of presence of strong metallic bonds. See, all are solid, which is clear from the picture. Transition metal crystallize in all the three face-centered cubic, then hexagonal closed pack. So this we have discussed in solid state. So different types of crystal structures are there, different names are there, and transition metals, as they are solid, so they can crystallize. They can crystallize in all these different possibilities. Along with metallic bonding, transition metals can also show covalent bonding. So metallic bonding, it is specially for metals, that is not observed for other elements. Suppose if you consider any non-metal, obviously metallic bonding is not present. But here sometimes covalent bonding is also possible, and it is because of this unfilled d orbital. So covalent bond means what? Suppose you have bond between X element and Y element. Now there are two electrons present in this bond. Now one electron is given by X, another one is given by Y, and after this donation, they are now equally sharing this electron. So this is covalent bonding, and this is observed in case of these elements. As they are metals, so they are good conductor of heat and electricity, which is also another property of metals. Okay, but remember, when you consider metals of group 1 and 2, that is, I'm talking about S block, you will hardly find them in free state, because that is the reason sodium, it is stored under oil or kerosene like this. Because if you keep it under open condition, there it is so unstable, there will be always a tendency to react with oxygen or moisture. But these metals are not like that. You can keep it. Just remember iron. It has versatile application in your day-to-day life, and it is so stable. But S block elements, you cannot get them under as free condition. You will even if you consider natural occurrence, you will see that they are mostly found in the compound form. That is, sodium, it is not found in the nature. That is natural occurrence. It is not sodium metal. It is NaCl like this. That is always +1 oxidation state. But these metals, though they are metals, but they are not so reactive like the metals that we see for S block. Okay. So is there any doubt? Some more atomic properties are also we have to discuss, are left actually. So regarding any slide in the whole class, if there is any doubt, please mention. Okay, so as there is no doubt, we are ending the session here. Thank you for listening.